Hi, my name is Betzaida Aponte-Hernandez. I'm a research assistant and a master's student. I'm working on this project with Edgar Rivera Valentin and Paul Schenk and Michelle Kirchhoff. So this project is a quantitative analysis that looks for agreeable processes that are affecting the morphological features on craters on Rhea. So basically, the motivation of this project is to use morphometric measurements to determine the dominant process governing this icy satellite. And so according to previous studies by White et al., they suggested this dominant process is to be relaxation due to past heat flow events. And as you can have noticed in the figures below, they ran tests from the calculation demonstrating relaxations on basins such as the Powehi, which is actually found on the area that we're studying. So basically, we want to see if the dominant process is this, and to see if this is the process that is governing Rhea. We're expecting to see like a linear relation between the diameter to depth and the crater wall slope. We're also keeping an eye on other processes such as crater infill and seismic shaking. So for anyone that isn't familiar with Rhea, Rhea is an icy rocky moon, and the Saturnian system is actually the second largest in the Saturnian system next to Titan, and it's found between Titan and Dione. And it's also just like our moon, it has a leading hemisphere and a trailing hemisphere. And a very peculiar thing that you can see in the trailing hemisphere is the chasm over here in the trailing hemisphere, and also over here as categorized as a fractured crater planes, which is this one here in the image on the left. In addition to this, just like any surfaces in the solar system, is heavily cratered. This map is actually provided by Paul Schenk. I'll be using this to illustrate the studied area. The area is that we're studying is located in the trailing hemisphere, and it's crossing the equator, but it's mostly on the northern area. This is the topography map that we're using. This topography map is actually also provided by Paul Schenk. It is based on high-resolution images from the Cassini spacecraft using photocalorimetry, stereo, and shadow length measurements. The mapping area is about 475,000 square kilometers, and it actually consists of some named craters such as Wakonda, Punta, Maheo, Kuksu, Gwojenji, Kuma, Botala, and the basin that I mentioned previously, Powehi. So now that we know the location, I'm going to be talking about how the measurements were done using Wakonda as the example. So we used the QView tool in ICES, and we measured the diameter and the depth of each of the crater by collecting 4 profiles. Each of these purple lines identify each of those profiles, which are separated by a 45-degree enhancement. And for larger craters, which are more complex craters like this Wakonda crater, we increased the profiles to up to 8. And just to take account the complexity of the depression. And in addition to this, we also wanted to include the rim and the surrounding terrain, so we extended all the profiles to at least a crater radius. Now, in this study, we defined the diameter as a measurement from the rim to the rim, and the depth as the measurement from the rim to the crater floor, or the lowest point of the crater. And we also calculated the crater wall slope by finding the least square feet slope of the topography from the rim to the nearest part of the crater floor. Now, keep in mind that I collected at least 4 profiles for each crater. This means that the determined diameter, depth, and the crater wall slope are mean values. Average and their errors are linked to their standard deviation. So once I collected the profiles of all the craters, I evaluated them and classified them as either simple craters or complex craters, where simple craters are basically straightforward bowl shapes or cone shapes. They are absent in any peak, center peak. And contrary to complex craters, they have a very obvious center peak, and they also have flat flooring. So now that we have the data collected and have classified it, we want to see what kind of story they can tell us. So also from here on, keep in mind, I'll be identifying simple craters with the color purple and the complex craters with the color cyan. So the first plot that we have here is a relationship between the diameter versus depth in a log scale. With an LSF line with a slope of 0.54 plus or minus 0.04. The largest diameter that we saw was actually Wakonda with 131 kilometers, and the smallest crater that we saw was 5.4 kilometers. So we are expecting to see mostly complex craters here because of the transition that was recorded by White et al. Has happened in around 5 kilometers. But we actually saw a pretty even amount of craters categorized as simple and complex as we see in this plot. So we also got the slope for the complex and simple, and we to verify our results, we compared it with the White alls, and we saw that we had comparable results with them. The simple, the second plot that we have here, I identified, we actually related depth to diameter ratio versus the equator wall slope, and we were able to find a DD of 0.1 plus or minus 0.3. DD is what I call here depth to diameter ratio, and the same as before, we were able to compare it with other results such as Rhea Valentin and Schenk, which they both got a 0.13 plus or minus 0.04. So now that we have these results and data, we want to see what we can do with it. And the first thing that we thought about doing with this data is to see what we can find as the simple to complex crater transition diameter. So this is actually when the simple crater starts to be in the minority and the complex crater start being the majority. And this is the diameter where we're trying to figure it out. We're using 3 different methods. The first method that we have uses the relation between the diameter and the depth, and we identify the biggest or the most significant change, and we found that this value was to be around 12 plus or minus 2 kilometers. The second method uses the topography information with the same plot as we saw before, except for this, in this case, we take into account the simple and the complex LSF lines, and whenever they had an intersection, that's the point where we call it the transition diameter, which occur in this case in 17.8 plus or minus 5 kilometers. The third method that we use uses a plot that relates the diameter bends in bends of 4 kilometers versus the fraction of simple craters. And the vertical error bars that we see here are from counting a statistic, while the horizontal error bars are from the bends. Here we take into account the crossing where the 50% of the craters are simple, and we found that the crossing occurs in between 5 to 22.5 kilometers. But LSF line here suggests that the intersection is an 18.8 plus or minus 5.1 kilometers. So we saw between the 3 methods that we collected, they suggest a range of 5 to 23 kilometers for the transition diameter, and the weighted average of this will be like 14.5 kilometers. This is actually quite similar to other icy rock surfaces. It is higher than previously reported, but it's similar to other studies with a transition at 15.5 kilometers, right, from Schenk et al. 1989-91. Now, take into account the gravity scaling laws for the transition diameter, and using the plot by Schenck et al., if we insert the values that we collected for Rhea, we're expecting it to be occurring around this range right here, which follows the trend of the transition versus surface gravity. Now, here we actually see again the diameter to depth ratio that we saw previously, with the exception that I added here the 95% confidence. Here we're trying to see what kind of modification process it's taking to the most of the craters, and we can see here that around 93% of the craters follow their linear trend, and a process that affects this simultaneously is actually a relaxation due to past heating events. But in addition to this, we see something that is not following that trend. So we're seeing two separate families here, like two outliers. And they're not following the same kind of trend, and they're very different. So we're going to be looking at them closely as separate families. So first off, we're going to be talking about the bottom outliers, which consist of 88% of the simple craters, and 12% of them are complex craters. So whatever is affecting these craters, it is affecting more often the simple craters. We also notice that these specific craters are shallow craters, which they tell us that it might be affected by ejecta infill or maybe seismic shaking. We also notice that there are slightly spatially related. We found that in the most crater location in the study region. So you can notice the proximity of the Wakanda and the Powehiwehi, which also suggests that there might be secondary craters. So looking closely at them using the method used by Michel Kirchhoff, we studied the craters' profiles and the topography and scaled them from 1 to 4. So we evaluated each of the profiles and the topography, and if we evaluate them with a number 1, it will be a fresh, pristine craters, while the number 4 will be a degraded craters. These craters were all evaluated in between 3 to 4, and we found the mode to be 4, which also agrees with the idea that these craters might be possibly secondary craters. Now, looking at the outliers from the top, we see that these craters are actually more common. They're more complex and simple, but still not so much of a difference as the previous one. We also see that they're steep craters, so we might think that these are junk craters. As you notice in the topography on the left, they're not spatially related. So we did the same thing, the same freshness examination to this family of craters, and we were able to see a mode of 2, which also agrees with the idea that these craters are younger craters, at the very least younger than the rest of the other families that we saw. So as a note of summary of what we found in this project, we were able to find a transition diameter occurring in a range from 5 to 24 kilometers, which we found the weighted average to be 14.5 kilometers. The 3 methods that we used gave very similar results to other icy bodies, such as Iapetus dianins, and which are very similar in size and position to Rhea. The inferred transition diameter is kind of higher than what we expected from a study report by White et al. From 2013, but this report was basically done through one simple method, and this actually supports the idea that multiple methods to validate the measurements is actually a good idea. So we think that using just the diameter versus depth plots might be biased to the transition diameter through smaller craters, which is why the transition is so small in that previous study by White, and ours are in higher diameters. And Our morphometrics studies actually supports the hypothesis of relaxation due to past heat events as a dominant modification process on Rhea. So as you may have noticed, that 92% of the craters that we study are in this kind of linear trend. So they support the white paper, and it also supports the bedding fill for the chasma in the trading hemisphere. It passes through the craters that we are in our area. We also found, in addition to this, 2 different families, and we are expecting that one of those families are junk craters, and the second might be another family of secondary craters. We have to look more closely to this to prove this, but that's what we have found. So thank you. I'll be taking questions, comments, ideas, suggestions.
Wonderful. Thank you. Thank you so much. We have plenty of time for questions. Thank you for staying on time. All the speakers have done wonderfully with that today. And we do have a question in the chat box. So Stuart, do you want to?
Sure. This one comes from Clark Chapman. You have a lot of small, complex craters, far smaller than the quote-unquote transition diameter. Is that because you, parenthesis, unusually define a flat-floored crater as complex?
Okay, so that could be one of the reasons, but in the beginning of this evaluation, I actually categorized the simple craters with flat flooring. It was later that I saw the study by Pike in the 80s that used the classification for flat flooring as complex as a transition stage. So in this case, I used that, but the transition did not change as much. So we didn't find that many flat floors, so it wasn't that significant when I tried it as simple and complex. But as the definition suggested by Pike, I try to follow the same kind of methodology for classification. Does that answer the question?
Yeah, so it looks like Jamie Riggs has some, and I think that she can unmute herself.
Hi. The next talk may address some of these, so we might want to hold some of this off until the discussion. But so you're claiming you have outliers. Are you assuming that the probability distribution function to determine that they're outliers is Gaussian? And if so, do you have evidence for that?
So I'm sorry. So we did see a distribution to be similar to the Gaussian. Maybe I work with this part of the point distribution function with Ed. Sorry, maybe this will help out. So maybe I should leave this to Edgar Villavantin, which is if you're there, maybe have a better response than I do.
Yeah, let me see if I can unmute him. I keep hitting the unmute
I believe
button.
I unmuted him, I believe. Ed.
Yes, I was typing a response, sorry, because I have a lot of background noise, but if y'all can hear me clearly. So I do hear your concern. We will be adding other tests to ensure that these are indeed outliers. For now, while we're working through this, we are defining them as outliers because they were outside of the 90% confidence.
Yeah, well, that's a little risky. Also, I mean, particularly because there's a clear skew to the right, to the high end. and that could mean that what you're claiming to be an outlier really isn't. But if you're going to do further work, then that takes care of that. I have another comment or question, if I may. You used SLR with least squares estimation to do the best fit. The issue there is the explanatory variable, which I presume was diameter, has errors, measurement errors among others probably. And the issue with SLR is that the predictors are assumed to not have error, and that the only error to be partitioned by the ANOVA in regression is on the response, which would be, I presume, depth. So I'm a little concerned that perhaps that fit might not be as accurate as you're showing.
Okay. Thank you for the suggestion. We'll take that to consideration.